Okay, so part two of our lesson on exponential function is going to deal with graphing these functions and the form. Remember the exponential form. If we have an exponential function, what makes an exponential function is the fact that our exponent contains a variable expression. And one of the things you're going to see also is that the base is a real number. So the base is a real number. Okay. Also, you're going to see that the base must be positive, so the base cannot be negative. The base must be positive. And also, the base cannot equal 1. So it can be any real number that's positive, but not 1. Okay? All right, so, and there's a reason why the base cannot be 1. So you're going to see that at some point. But let's first of all start graphing. We're gonna graph an easier exponential function first, and then we're going to look at characteristics about that function. Okay? All right, so the first one we're going to do is let's go ahead and have a discussion about graphing f of x equal, let's say, 2 to the x. All right, we're going to start with a simple one. F of x equal 2 to the x. All right, now we're going to go ahead and do this by using a t-table. And then we're going to plot these points in the coordinate plane. And so exponential functions rises very rapidly. So usually, sometimes if you Google viruses and exponential functions, you'll see that, and it's mostly the first quadrant because the time is usually on the x-axis and it's positive. So if you Google viruses and exponential functions, you'll see that this is the part that's usually graphed, and the graph looks something like this. So you're going to see what the graph's going to look like, and it rises very rapidly. Okay? All right. So if I look at f of x equals 2 to the x, I'm going to use a t-table. I'm just going to plot some points for right now. Okay? So for example, if x is, and remember, x can be any real number. It can be positive, it can be negative. Okay? So if x is, let's say, 0, I'm going to look at 0 and some positive numbers for right now. So if x is 0, I get 2 to the 0, which is 1. Okay? So I'm going to plot the point 0, 1. And as I do that, we're going to have a discussion. So here's the point 0, 1. All right? If x is, let's say, 1, I get 2 to the first, which is 2. So I'm going to plot the point 1, 2. So 1, 2 is right here. Okay? If x is, let's say, 2, I get 2 squared, which is 4. So I'm going to plot the point 2, 4. Now, don't assume this looks like a quadratic function. It looks like a parabola. All right? So it's not. This is not a parabola. So 2, 4 is here. So don't all of a sudden do something that looks like a parabola. Okay? It is not. This is not a quadratic function. This is a exponential function where the base is 2. If x is 3, I get 2 cubes. Ooh, excuse me, 2 cubed, which is 8, right? So 3, 8. So 3, 8 is here. Okay? All right, just follow along for right now. If x is, let's say, 4, I get 2 to the 4th, which is 16. And then I'm going to stop there in terms of that because everything else, if I use any more values for x beyond 4, it'll be outside this coordinate plane. But if x is 4, I get y is 16. So I get something up here. All right. So this part of the graph looks like this. All right. So I'm going to go ahead and just start graphing this part of the graph. Okay. So it rises very rapidly. You see that? And so if I were to look at, let's say, 5, which I'm not going to plot because I don't have enough room. But if I look at x equal y, if x is 5, I get 2 to the 5th, which is 32. So basically, what's happening, if you notice that since the base is 2, each of these is doubling. Each of these y values are doubling. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. And then you see it keeps doubling. All right, so if you look at again, viruses, you'll notice that in some cities and states, it's doubling. So that would be an exponential function. Okay. All right. Now, hopefully, so remember what we're trying to do is trying to flatten that curve. So instead of being an exponential function at some point, because the exponential function continues on doubling each time. And so, in this case, doubling because it's 2. If it's 3, it'll be tripling, okay? In this case, it's 2. But we want this thing to flatten in terms of viruses. Okay. But anyway, so if x is, let's say, 6, what do you think will be without having to do this? You just say times 2, right? So 2 to the 6 would be 64. So you see it keeps getting steeper and steeper and steeper and steeper. All right. Now, so that's what happens on this side. So as from 0 to infinity, see from 0 to infinity, my y values are getting bigger and bigger and bigger. Y'all agree? That's important to see. All right. That's important to see with this particular one right here. So look at what we're doing. All right. So notice it keeps doubling. Why is it doubling? That's important. Why are these y values doubling each time for each increment of 1 here? 1, 2, 3, 4, 5, 6. Why is it doubling each time? Because of your base. All right? Because of that base. Okay, now listen carefully. Let's talk about what happens on this side. Okay, so I use positive numbers. Now let's use negative numbers. All right, so that's where your calculator may be important for some of you. If x is -1, I get 2 to the -1. Now, some of you may remember from a previous course, either Math 98 or some other high school course you may have taken. Others of you may not remember that. That's okay. But when you have a negative exponent, I can make that exponent positive by taking the reciprocal of that of the base. So the reciprocal of 2 is 1/2, and so that becomes 1/2 to the first power, which is 1/2. So 2 to the -1 is 1/2. And so if you didn't know that, then just use your calculator. And that's what we're going to do here because we don't have time to actually go through all this work. But if you use your calculator, you'll say 2 raised to the -1 power, see how that looks, equal, you get 0.5, which is 1/2. All right, so 1/2. Okay, if x is -2, let's see what happens. So I get 2 to the -2. And again, let's just have the discussion, then we'll use a calculator. So if I want to make that exponent positive, I got to take the reciprocal of the base. The reciprocal of 2 is 1/2, and I'm going to square it. So now my exponent's positive. 1/2 times 1/2 is 1/4. Okay? So 1/4. And let's check it. So 2 raised to the -2nd power equals 0.25, which is 1/4. All right, so I'm going to go ahead and start plotting this. So when x is -1, look at this carefully. When x is -1, I get 1/2, right? It looks like this so far. When x is -2, I get 1/4. See it? Okay. Now, here's my question before we go any further. When x is more negative, I said more negative, but as x gets negative and negative and negative, this way, -3, -4, -5, will my y value ever be positive? I'm sorry, ever be negative, excuse me. Will this ever be negative? Well, let's think about that. Okay, so here's the question. Will the graph ever go below the x-axis for this function I'm graphing? Will the graph go below the x-axis? So if it goes below the x-axis, that means my y values are negative, right? If it goes below the x-axis, that means your y values are negative, okay? Will my y value here ever be negative? Look, they're all positive. So I'm asking you, will this ever be negative? No, because you look at your base. Your base is positive. A positive number raised to any power, whether it's negative, 0, or positive, is always positive. So this is never going to be negative. So here, my y value is never negative. Okay? for what I have here, that y value is never negative. All right, so as we graph this, as we go further this way, I want you to notice that it's not going to cross the x-axis. Now, my next question is this. Is there, and that's going to be our discussion, is there a y-intercept for this function? Okay, so is there a y-intercept for this function? Meaning, I didn't mean y-intercept, excuse me, x-intercept. There is a y-intercept, we found it, right? So yes, there is a y-intercept, but I mean x-intercept. So is there an x-intercept for this function? Is the graph going to touch the x-axis? Okay, that's going to be our question. All right. So the idea would be this, and then we're going to talk about it. So remember in previous lessons, to find the x-intercept, you let y equal 0. Remember that? Well, what is y here? Well, y is f of x. So I'm going to let this be 0. So the question is this: is 2 to the x ever going to be 0? That's a question. Is 2 to the x ever going to be 0? Well, remember, 2 to a positive number, you know that's never going to be 0. 2 to the negative number, you know that's never going to be 0. And you might ask, well, what about 2 to 0? We already found that. 2 to 0 is what? 1. So is this ever going to be 0? No. So this has no x-intercepts. So this function has no x-intercepts. This function has no x-intercepts. Okay? So then that brings us to this. Then what does this look like then? What does this look like? Well, let's continue on with a couple more points. If x is negative 3, use your calculator. We have 2 to the negative third power, and we're going to use a decimal here. So 2 raised to the negative third power equals 0.125. Okay, so 0.125. So I want you to notice these, I'm going to put these as decimals, 0.5, 0.25. What do you notice about these y values? They're getting smaller, right? Here, as x became more positive, as x went to infinity, let's talk about it that way. As x goes to infinity, these y values get bigger. As x goes to negative infinity, these y values do what? They get smaller. See that? So kind of like it's doing this. You'll see this. So for a negative 3, I got something closer and closer to 0. So it looks like it does this, but it never touches the x-axis, because we just said that this function has no x-intercept. And it never goes below the x-axis, because if it did, first of all, it would have an x-intercept. Secondly, the y values would be negative, and we saw here that all these y values are positive because I'm taking the base 2, and the base is always positive, right? So the base 2, we just talked about that, the base is always positive. A positive number raised to any power, any exponent, is always going to be positive. So that takes us to this. So first of all, this is what the graph looks like. Okay? That's what the graph looks like. So that's what an exponential function looks like. A quadratic function is not as steep, but on this side does this. Remember that? This is an exponential. Okay, so on one side, this is important to remember, on one side it looked like it flattens out. It doesn't, because these y values get smaller and smaller and smaller and smaller. All right? Now, when you graph this, do not make it look like it crosses the x-axis. That's important. When graphing this function, do not make it look like it crosses the x-axis. Do not make the graph look like it crosses the x-axis, because it has no x-intercepts. All right. So you just kind of draw it a little on here, and then you draw your arrow like that. Okay, now let's talk about something else that's important. Every exponential function every exponential function has a horizontal asymptote. All right, so every horizontal function has a horizontal asymptote. All right, so let's talk about what I mean by horizontal asymptote. So horizontal asymptote, in this case, if you look at these, so you see how it kind of flattens out on this side? On this side, it rises rapidly. So where I'm using the word flatten, it doesn't go become a straight line now. Okay, when I say flatten, I don't mean that. I mean the y values are getting smaller and smaller and smaller. So the side where the graph kind of looks like it's flattening, it's approaching a horizontal asymptote. It's approaching a horizontal asymptote. It's approaching a y value. And I want you to notice this right here. What is the y value that this is getting closer and closer to? So if I do, let's say, -8, I get y to the -8, right? So I'm sorry, I get -2 to the -8, excuse me, 2 to the -8. So 2 to the -8 equals 0.004. If I approximate this, 0.004, I'm approximating this. It's getting closer and closer to what? It's getting closer and closer to 0. So as x approaches negative infinity, my y value approaches 0. It never becomes 0. It approaches 0. So your horizontal asymptote is a horizontal line. And remember how we denote a horizontal line? We say y equals. A vertical line is x equal. Remember that? So a horizontal line is y equal. And in this case, it's y equals 0, the x-axis. So your horizontal asymptote is the x-axis. In other words, this at part of the graph, the one that flattens out gets closer and closer to the x-axis, but never touches it. So your horizontal asymptote is the x-axis. And when you graph these, you're going to denote the x-axis. You're going to denote the horizontal asymptote as a dotted line. So you're going to do this. Just put a dotted line. Remember when you did the axis of symmetry for a quadratic function, you did a dotted line? Same thing here. So you kind of do a dotted line like this. Okay? All right, well, let's talk about some things about this. All right, so now when graphing these, you're not going to graph that many points. We use that many points for right now just to kind of have a discussion about what a exponential function looks like. So notice that on one side, it looks like it flattens out, although it doesn't. Okay, make sure you draw an arrow. Make sure that it does, when you graph it, it does not touch or cross the horizontal asymptote. And on the other side, it rises rapidly. Okay, it rises rapidly. All right, now let's have some discussion about other ideas about this particular function. Okay, so let's talk about domain and range. All right, so for this same one, we're going to talk about domain and range. Looking at the graph, let's talk about domain and range. So we're still talking about f of x equal 2 to the x. F of x equal 2 to the x. Let's talk about domain, range. So those are the questions you're going to be asked. So when you look at your worksheets, you're going to be asked to find the horizontal asymptote, the domain, the range, and the y-intercept. Okay? All right, so domain and range first. Let's talk about that. So we're going to use our ruler, just like we did with previous graphs. And let's go about the domain first. So notice my domain. See, this is an arrow that goes this way, right? So when x is negative, whatever this value is, am I going to get a point on the graph? Sure I will. It'll be very, very close to 0, but I'll still get a point on the graph. So do y'all see I'm going from negative infinity all the way to positive infinity? So when x is, let's say, 1,000, I'm going to get a point on the graph. Will be way up here, though, right? Okay. So, and from the t-table, you can see that I can use any value for x. 100 million, 1 billion, negative 1 billion, and so on. And I'll get a y value. So it turns out one of the properties for exponential functions that's important for you to remember now. So every exponential function has a horizontal asymptote. Every exponential function, the domain is all real numbers. So as in, remember in interval notation, that means this, negative infinity to infinity. So the domain of every exponential function is going to be all real numbers. I can use any value for x. So here you're going to say negative infinity to infinity. But the range is not the case. It's just like when we did the quadratic function. Remember the domain of all polynomial functions are real numbers, but the range depended on where the vertex is. So remember when we graphed the exponential functions? Real quickly. I'll just kind of do this real quick. So when we graph exponential functions, remember the domain was all real numbers. So all polynomial functions, remember we talked about that, all polynomial functions the domain is all real numbers. But the range wasn't the case. The range depended on where the vertex was and whether the problem opened up or down, right? So in this case, we would say the range would be from -5, the range, bracket -5 to infinity. All right, notice the bracket here. That's important. And we're going to talk about what's going to happen with the exponential. But here, the range is bracket -5 because that point is on the graph. -5 to infinity. All right, now let's talk about the range of an exponential. All right, now listen carefully. This is going to be important. Do y'all see that my range is not 0 to infinity, bracket 0? All right, because my y value is never going to be 0 here, right? It gets closer and closer to 0. So and in your horizontal asymptote here, and let's go ahead and write it, horizontal asymptote. The horizontal asymptote is y equals 0. Okay, so always denote the horizontal asymptote. Every exponential function has a horizontal asymptote, and we're going to denote it as y equal some number a. Okay, whatever a may be. All right, so in this case, it's y equals 0, and you're going to see how we get this in a little while. All right, so y equals 0. So then the range then will be from that horizontal asymptote. So I'm going from 0, but remember, 0 is not part of the graph because my y value is never going to be 0. So for this one, we use parentheses. That's important. Parentheses 0 to all the way to infinity. So again, remember for a quadratic function, the range we did a bracket because that was part of the graph. Negative, when y is -5, I get a point on the graph right here. So that's why it's bracket. Here is parentheses because this horizontal asymptote, my y, which is the x-axis, and y is 0 on the x-axis, but my y coordinates here is never 0. It gets closer and closer to the horizontal asymptote. So if I go back to that t-table, is this right here, as I go to negative infinity, will my y values ever be 0? No, it'll get closer and closer and closer to 0 without equaling 0. It approaches 0 without being 0. Okay, and then the other thing you're going to be asked to do is find the y-intercept, which you already found. So my y-intercept here as an ordered pair, y-intercept here as an ordered pair is 0, 1. All right. Okay, so those are going to be the things you'll be asked to do. All right, now let's look at another problem. All right, so that was a lot of discussion on just y equal 2 to the x. Okay. Okay, now we're going to come back. We're going to come back to in a little while and talk about a better way of finding the y the horizontal asymptote without having to use a t-table. There is another way to find or to determine very quickly in half a second what your horizontal asymptote is. All right, so we're going to have another discussion though, and then you'll see what it is, how to find it. Okay, so we graphed y equal 2 to the x, right? So let's go ahead and graph this one then. Let's look at this one. So let's go ahead and graph y equal or f of x equal, let's make it g of x. G of x equal 2 to the x minus, let's say, 4. 2 to the x minus 4. Okay? 2 to the x minus 4. Okay, so we're going to use a t-table. We're going to have that discussion again as we go through this, and we're going to plot our points. All right, so let me go ahead and get a grid paper. Okay, so using a t-table, and notice that this is exponential. My base is 2. It's positive. It's not 1. And my variable expression is in the exponent. And notice this negative 4 right here. So here, I didn't have a constant added to this. All I had was 2 to the x. Here I have 2 to the x minus 4. I wonder what that does. All right, let's see. If x is 0, so remember when I let x be 0, I'm going to have a y-intercept, right? So remember to find the y-intercept, you let x be 0. So another thing I want you to know now is this. Every exponential function has a y-intercept. And remember to find the y-intercept, you let x be 0. And you might say, well, why does it always have a y-intercept? Because what's the domain? Domain is all real numbers, isn't it? So in x equals 0 in this domain, so it's going to have a y-intercept. And so to find the y-intercept, you just let x be 0. So let's go ahead and find the y-intercept right away. So the y-intercept is going to be 2 to the 0 minus 4. 2 to the 0 is 1. 1 minus 4 is a negative 3. So I found the y-intercept of my graph. So y equal negative 3 right here. So there's the y-intercept right here. Okay? All right, so let's now just use some positive values for x right now. If x is, let's say, 1, I get 2 to the first power minus 4. 2 minus 4 is a negative 2. So I'm going to plot the point 1, negative 2. Okay? 1, negative 2. Right here. Okay? If x is, let's say, 2, I get 2 squared minus 4. 4 minus 4 is 0. Okay? So I'm going to plot the point 2, 0. Now in this case, I do have an x-intercept. Okay, so one of the other things I want you to remember is this. So every exponential function has a horizontal asymptote. Domain's all real numbers. It's always going to have a y-intercept, and find you let x be 0. And it may not have an x-intercept. Okay, and you don't have to find, you have to find the y-intercept because that's easy to do, but you don't always, you may not be asked to find it. You don't have to find it. You don't have to use it to graph. Okay? All right, so let's do a couple more points on this side, because remember, you know what an exponential function looks like. So exponential function, a graph looks like this. So it rises rapidly on one side and then flattens out. It looks like it flattens out, but it gets closer. It's actually decreasing, but it gets closer and closer to whatever the horizontal asymptote is. Okay. Now you can also see it could do this. So it rises rapidly on this side, and then it flattens. Looks like it flattens out on that side, right? Now, one point you also see it will do this. So if this is your horizontal asymptote here, it could do this. But the point being that in one part it either rises rapidly or it falls rapidly. Rises rapidly as you go from, in this case, to infinity, in this case negative infinity. Here as you go to infinity, your graph falls rapidly. Okay, or it could do this. So as it goes to negative infinity, it falls rapidly. Okay, all right. So those are the scenarios you're going to see. Okay, so let's do x equals 3. So if x equals 3, I get 2 cubed minus 4, which is 8 minus 4, which is 4. Okay, so 3, 4. Okay, so 3, 4. So let's say that's here. So this side kind of looks like this for right now, right? Okay, so I can go ahead and kind of do that part. Now let's see what happens on this side. So if x is negative 1, I get 2 to the negative 1 minus 4. Use your calculator, use the decimal. 2 to negative 1, and then minus 4 equal negative 3.5. All right, so I'm going to put the point, negative 3.5. So that's about, so negative 1, negative 3.5 is here. You'll see that? Okay. All right, now, if x is, let's say, negative 3, I'm going to go to negative 3 for right now. I get 2 to the negative third power minus 4, which is, let's see what that is. 2 to the negative third minus 4. So 2 raised to the negative third minus 4 equal negative 3.875. Negative 3.875. Yeah, all right, so that's looking like, I said negative 3, so it looks like it's about right here, right? Okay, so here's my question to you. And think about this. As x goes to negative infinity, so as I approach to negative infinity, what is the y value of your function approaching? So what is this approaching, do you think? What do you think? So if I put, let's say, negative 12 here, negative 12, and I have 2 to the negative 12 minus 4. Let's see what that is. 2 to the negative 12 minus 4 equal negative 3.9997 and so on in it. What do you think it's approaching, guys? It's approaching negative 4, isn't it? It's approaching negative 4. So that's going to be your your horizontal asymptote. So my horizontal asymptote, A-S-Y-M-P-T-O-T-E, your horizontal asymptote is a horizontal line, so you can say y equal that number, y equal negative 4. Now here's my question. Do you see that number, negative 4, anywhere in your function? Yes, you do. It's right here. That is always going to be your your horizontal asymptote. This right here. Your horizontal asymptote is always going to be this. Okay? So, y equal negative 4 is your horizontal asymptote. Now, here's what I want you to do. I want you to denote that using a dotted line, just like this, on negative 4. See negative 4? So you can put a dotted line. And then what you're going to do is use that to help you draw your graph to where it looks like it's going towards the horizontal asymptote with an arrow without crossing it or touching it. Okay? So your y values will never be below negative 4. Will never be below the horizontal asymptote. So that's what your graph looks like. So that is g of x equal 2 to the x minus 4. All right, so now you know this. Now you know this. Okay, so for these two functions right here, for these two functions, your horizontal asymptote is going to be this number. Okay, so your horizontal asymptote, when I had y equal a, I'm going to say y equal c. Your horizontal asymptote is going to be y equals c, that number. So you might say, well, how did it get 0 here? Because remember when we did 2 to the x? 2 to the x. Let me go ahead and write it right here. When I did 2 to the x, when I graphed y equal 2 to the x, do y'all agree? Do y'all agree when I graph y equal 2 to the x that that's the same thing as saying f of x equal 2 to the x plus 0? So there's your y, your horizontal asymptote. So my horizontal asymptote, I'm going to note HA. Your horizontal asymptote is y equals 0. So my function is this. H of x equal 5 to the x minus 10. What is your horizontal asymptote? What's a horizontal asymptote? So your y values, we are closer and closer to what number? Negative 10. So your horizontal asymptote is y equal negative 10. If I have k of x equal 1/3 to the x plus 3 plus 6, what's your horizontal asymptote? It's that number right here, 6, positive 6. So your horizontal asymptote is y equals 6. All right, so now you know how to find the horizontal asymptote, right? Okay, now let's kind of do this in a much quicker version. So notice that both problems took a little bit long to do, but here's how you're going to deal with this. Oh, first of all, also I forgot to go back and finish that one. So let's go back and finish this. So let's talk about the domain. So I'm going to find the domain, range. We already found the horizontal asymptote, and I already know the y-intercept. The y-intercept is 0, negative 3. 0, negative 3. You're always going to have a y-intercept. Okay, the domain. So remember the domain, what's the domain of all exponential functions? The domain of all exponential functions is what? It's all real numbers. You can even look at your graph and see it's all going to be real numbers. So if x is negative 1 million, I'm going to get a point on the graph. And so from negative infinity all the way to infinity. Now your range is where it is not all real numbers. Domain's all real numbers. Your range is not. So remember, you're going to go from bottom up, just like you did before. So you start touching the graph kind of when you get to the horizontal asymptote, right? Now my horizontal asymptote is y equal negative 4 in this case. Will my y value, will any point here ever have a y value of negative 4? No. It approaches negative 4, but it doesn't. You just notice that here we got negative 3.999 and so on. So as you get closer and closer to negative infinity, it gets closer and closer to negative 4 without actually being negative 4. Okay, the other thing you got to know that you're going to say negative 4 to infinity, and here's where students mess up. They know it's negative 4 to infinity, but they put a bracket. It's not supposed to be a bracket. What is it supposed to be? Parentheses, negative 4 to infinity, because none of these y values are ever going to be negative 4. Okay? All right, now. Okay, so now let's look at another problem, but let's see if we can graph and find this information in a much quicker way. All right, so here's the idea. When you look at the worksheet, it's going to say this. It's going to say graph the following functions, and they're going to be exponential, and draw the horizontal asymptote. Okay, so the horizontal asymptote, and then plot at least 3 points. Now notice here, in the first one, I plotted a lot of points, didn't I? I didn't need all that. I did not need all those points. Okay. All right. So here's what I would do. Okay. So let's do another example, and we're going to see how we can do this in a quicker way. All right. So let's go ahead and graph g of x equal, let's say, 3 to the x minus 5, let's say. 3 to the x minus 5, okay? So let's graph that. All right, well, the first thing I'm going to do is right away, I know what my horizontal asymptote is. What's the horizontal asymptote? Well, the horizontal asymptote is y equals negative 5, right? So right away, and we'll go ahead and get a grid paper, right away, I can draw my horizontal asymptote. That's the first thing I would do. So let's go ahead and draw the horizontal asymptote. So y equal negative 5. It's a dotted line, right? Horizontal dotted line. Here's negative 5. So let's go ahead and draw this dotted line. Okay? All right. Next thing I would do is I would find the y-intercept. So let's find the y-intercept. Remember, you always have a y-intercept. So the y-intercept, you're going to let x be 0. So if x is 0, I get 3 to the 0 minus 4. 3 to the 0 is 1. 1 minus 4 is negative 3. Okay? All right. So 0, negative 3 right here. Y'all. Oops. Yeah. Oh, I'm sorry. That should be minus 5. Excuse me. So that's negative 4. Okay, so 0, negative 4. Right here. Then what I would do then is I would pick, remember you want 3 points, right? So I already have 1. Pick 2 more on this side, and let's see what happens. Okay, listen carefully. If x is 1, I get 3 to the first minus 5, right? So 3 to the first is 3. 3 minus 5 is negative 2. So I'm going to plot the point 1, negative 2. Look how quick this is becoming. Okay, I need 1 more. If x is, let's say, 3, I get 3 cubed. Oh, that's going to be too much. Let's say 2. That's going to be too much because, look, 3 cubed, 3 times 3 times 3 is 27. 27 minus 5. 27 minus 5 is going to equal 22, right? Which is way beyond this. So let's do 2. All right, if x is 2, I get 3 squared minus 5. So that's 9 minus 5, which is 4. I get the point 2, 4. Right here. All right, now, that's all you needed because, look, you know on one side the graph rises rapidly, right? Like that. Make it look like that. And on the other side, it gets closer and closer to the x-axis. I'm sorry, to the horizontal asymptote. And there you go. You're done. That's your graph. See how quick that was? All right, so you do one side, and the part that goes towards the horizontal asymptote, you just make it look like it goes towards the horizontal asymptote. Get closer and closer to it. Now, don't all of a sudden make it look like it goes up, okay? Do not draw your graph to where the arrow kind of points up like this. Just make sure it goes down like this, okay? Do not. So if you do, it means you're not listening to this part of the video. Do not make it look like it does this, because it does not. It goes towards this, so be careful. Don't be lazy. Okay? Will it ever cross the horizontal asymptote? No. All right, so it approaches this negative 4, but without touching it. And there's your graph. And so now you can answer the other questions. Okay, so that's all you needed. Now you can answer the other questions. The domain, remember it's an exponential, so what's the domain? All real numbers. What's the y-intercept? You already found it. That's the one thing you're always going to find is the y-intercept, 0, negative 3. Okay, now here's the other thing you got to find, the range. And you already found the horizontal asymptote, so the horizontal asymptote is y equal negative 5. Don't put negative 5. Remember how some of you, when you graph your quadratic functions and you're asked to find the axis symmetry and all you put was negative 5, you lost some points, right? Remember, the axis symmetry, the horizontal asymptote, those are lines, so denoted as a line, an equation. The range, now this is where somebody's going to mess up, so be careful. So the range, you're going to go from your horizontal asymptote, which is in this case negative 5, right? Now, here's the question. Is it bracket or parentheses negative 5? It's parentheses, negative 5 to infinity. In fact, if you think about this, for every horizontal, for every range of the exponential function, for every exponential function, your range, this is always going to be parentheses. Okay? Always going to be parentheses. Okay, so that should, we're at 45 minutes now, so that should be, give you a little bit of conceptual understanding on how to graph exponential functions. Notice this is where you want to end up. You want to end up graphing it just like this very quickly. And then finding the domain, range, horizontal asymptote. You always have a horizontal asymptote. The domain's always going to be all real numbers, and the range depends on where your horizontal asymptote is. And your y-intercept, you always have a y-intercept. That's the first point you're always going to find. Let x be 0. Okay? All right, so we're going to look at a few more examples in the next part, but that should help you somewhat. All right, so that's the end of part 2.